Welcome back. Now that we finished our unit on trigonometry, we can move into something a lot more exciting, which is trig functions. I know you've all been waiting for this. I actually do find it more interesting than trig itself. Trig is nice for grade 9 and 10, but we're the big people now, so it's time for some trig functions. Specifically today, we're going to take a quick look at graphs of sine, cos, and tan. Not that these may be new to you. You may have covered these in grade 11 or the MCT course, depending on which one you took. But we are going to take a look at a few ways of doing new things with them this unit that we haven't done before. Let's start off by just doing a quick little review of transformations. So you probably recall we could deal with a function, but kind of like that top one there, which is a polynomial function. In fact, it's just a quadratic. And in fact, we can actually use that to answer part A, which what is the base function? And the base function is just f of x equals x squared. So that's the base function, and then there's been a whole lot of little transformations that have happened to that one that are going to modify what the graph would look like or what the function itself does. So just as a quick reminder, what do each of those things do? Well, the -3 at the front does a few things. It actually does two, one because of its sign, one because of its value. And it does a vertical stretch, which I'm just going to put down v stretch for short. And it also does a vertical flip, which I'm going to use v flip for short. The 4 inside the bracket in front of the x part, that 4 is going to cause a horizontal compression. And you could put down by a factor of 4 if you'd like, in much the same way that the vertical stretch I could have said by a factor of 3. But either way, it is going to be a compression. The x minus 5. The minus 5, and I got to be careful about this because technically the variable is x minus d, and d is 5. But I just want to be clear that the minus 5 after the x actually will move to the right. So I'll just put down right 5. And finally, the -6 at the end is going to be another translation, except this time it is going to be a vertical translation, and it's going to be down 6. Okay, so hopefully that all rings a bell. We didn't cover that long ago. Now let's move into some actual trig function stuff. A few things first. Let's talk about the amplitude of a function. And this applies to periodic functions. So that's functions that look like this, where they just go up and down and up and down. Technically, the tan function does not do that, but the sine and the cos both do. And we'll look at them in a little bit more detail in just a moment, but I want to make sure we know what these words mean first. The amplitude is the height of a periodic function above or below the rest point. Now, if you think about water, this is the easiest way to think about it. Water as being kind of a flat surface. That's what we'll call the rest point or rest position. And then I want you to think about waves in water. They don't just go above the water. That would just be creating new water. They go above and below. And so what we actually get is an amplitude, and it's the distance like this that's above. Oh, actually, you know what? I think I'm going to use an uppercase A just so it doesn't get confused. Actually, you know what? No. Let's use a lowercase a for amplitude, and it can be above or below. So technically the total height of the wave from top to bottom is actually 2 amplitudes, not 1. That's a common mistake. Period is the time it takes to complete one full wave. And I'll draw a picture so that becomes more clear. If I have something that's periodic, I could define one full wave as the distance between the two tops, or I could define it as the distance between the wave and where it starts to repeat itself, or I can go from bottom to bottom. It doesn't matter. Those should all be the same lengths. And just to be clear, for those of you who have taken physics or just know this, the actual distance in meters or centimeters is called the wavelength. This is specifically the time that it takes to get from one point to the next. So for instance, if you're sitting in a boat watching a wave and you see a big crest pass by you, the top of a wave, and then you count until the next big one comes and hits you, that's going to be the period, the time. And I will make a little note here that we often denote the period as capital letter T. It is a time, but it's a time of a specific thing. It's a time of a wave. Phase shift. Phase shift, we actually already have a word for this, or a term for this that we've been using. And this is just a horizontal translation. So for instance, if we have a wave that does this, and then I move it over a little bit, this distance that it moves here is the phase shift. So this is just a new term that we use for a horizontal translation. So instead of saying, for instance, in the one that we just did, we talked about going right 5. Here, instead of saying right 5, we would say it has a phase shift of whatever that distance is. This is just a commonly used term in physics and in the physical sciences. So let's take a look at f of x equals sine x. I'm just going to draw this on the graph. And by all means, you can, sorry, just have pen trouble here. Stick it, there we are. By all means, feel free to use Desmos if you want a little bit of help on what this would look like. But I'll tell you right now, the sine curve, it has a 0 there. And by the time it gets to pi over 2 or 90 degrees, it goes up to 1. At pi or 180 degrees, it goes back to 0, and then negative 1, and then 0. And it should look something like this. And my graph is not going to be perfectly drawn because it's hand drawn, but that's okay. I'll try to make it as nice and smooth as possible. So it should look something like that. So looking at that base sine function, let's just fill in some of the information about it that we sometimes want to know about these waves or trig functions. The first of all would be the maximum. The maximum is the highest it goes to. That occurs right there. So we can say the maximum is 1. The minimum occurs down here. That would be negative 1. The amplitude is the distance above or below the rest position, or the middle point. So in this case, it's 1. It goes up 1 from 0 and down 1 from 0. Its period, starting here, it doesn't repeat its pattern until it gets over to 2 pi. So its period will be 2 pi. And I'll put down in here, it's 360 degrees if you're measuring it in degrees. Phase shift is 0 regardless of whether you're measuring it in radians or degrees. And its vertical translation is 0 because it's not above or below the x-axis. So now let's take a look at a trig function that does have a few changes made to it. Specifically, f of x equals negative 2 cos x, negative 2 cos bracket 3 bracket x minus pi over 2 bracket bracket plus 1. Okay, so before we actually write these out, let's just remind ourselves what each of these things does. I won't write them out in words, but I will say them. The -2 at the beginning causes a stretch vertically of 2, and the negative flips it upside down. The 3 in front causes a compression of factor of 3 sideways or horizontally. So basically it squishes it side to side like an accordion. The minus pi over 2 is going to shift it right pi over 2 or 90 degrees. And the plus 1 at the end is going to move it up 1. So from that, can we figure out what the max, min, amplitude, and everything else are going to be? Okay. The maximum. The maximum is going to be the rest position, which is moved up 1, with an amplitude of 2. So it's actually going to go up from 1 to 3. I'm going to just switch this back to blue. The minimum, it shifts up 1, but it goes, it's amplitude of 2, so it'll go down to -1. The amplitude is 2. A common misconception is that it is -2 because there's a -2 in front. The amplitude is still 2 in magnitude. The fact that there's a flip is completely separate from it. The period. Okay. What we saw above is a normal trig function, sine or cos at least, just because they're extremely similar, will normally, just recall this up here, have a period of 2 pi. It repeats every 2 pi or 360 degrees. This one, however, has this factor of 3 that squishes it down. So instead of repeating every 2 pi, it's going to repeat every 2 pi over 3, or every 120 degrees. I guess that kind of makes sense, right? Normally it would go over 360. It's crushed by a factor of 3, so it's now going to complete a period over 120 degrees. The phase shift. I think we already mentioned there, the x minus pi over 2 means it's going to go right pi over 2. And the vertical translation is basically just saying, does it go up or down? And it goes up 1. So can we draw this? Okay, this is going to get a little tricky. I'm going to start by drawing just a base cos function. Base cos function goes from 1 to 0 to -1 to 0 to 1. I think the next thing I'll apply, maybe with a slightly different color there, orangey color, to complement the yellow, I'm going to apply the flip and the vertical stretch by a factor of 2. So the 1 goes down to -2, 0 stays 0, -1 goes up to +2, and this goes back to 0 and down to -2. So now we do this. And I should point out that we always have to do our stretches and our compressions first. It doesn't actually matter which order you do them in, as long as you do them first before any of the translation stuff. I guess really quickly I can write here that this part, where do I want to write this? Write it right here. This would be cos, sorry, negative 2 cos x. The original one would be cos x. Okay, now I want to deal with that 3. So let's go to red. And I want to compress this by a factor of 3. So everything's going to be about 1/3 of what it used to be. Well, that's not going anywhere side to side because it's already at 0. This scale on here is not the best for what I'm trying to do, but it'll have to do. So 1/3 of our point here takes us to about 1 1/3. It's actually 4 grid boxes. Now it's 1 1/3 grid boxes. The maximum point up at 2 has to go to 1/3 of 8 boxes, which is 2 2/3. About there. This point will come over to here. 12 boxes becomes 4, and 16 boxes becomes 5 1/3. And at this point, I could repeat that pattern a little bit. It's a little bit tricky, but I think it's going to look something like this. Go away. I swear I've turned on every possible thing I can to make notifications go away, and somehow they still squeak through. I'm starting to get a little bit messy here, but that's okay. I could keep going, but I think you already see the pattern by this point. And now that one's going to be negative 2 cos 3x. And I think at this point I can do both of the remaining things at once. I can move it right pi over 2 and up 1. So I'm going to take this point down here, and I'm going to move it over pi over 2, right pi over 2, and up 1. I'm going to take this point and move it over pi over 2 and up 1. This point goes over pi over 2, up 1. Where are we? This point, pi over 2 plus 1. This point, pi over 2 plus 1. And this point, pi over 2. Ooh, losing track in my head here. Plus 1. So I think there's enough here to say it's going to do something like this. And I'll tell you right now, I'm not at all confident that I didn't go off a little bit on one of those points. But that right there should roughly be negative 2 cos 3 x minus pi over 2 plus 1. And if you want, we can always go over to Desmos and verify it. But I'll leave that to you if you want to try it. If you'd like, just pause it, go over, try it, and come back. Okay. This one here is less of an example and more of just trying to point out to you that there's an extremely common error that students make. And I want to try and catch you before you make that error. And that's if I give you that function there, f at x equals cos negative 2x plus pi over 3. What's the phase shift on that? Now, I want you to think about that for a second. And if you said left pi over 3 that is not the correct answer. It's the one I get most commonly on tests, but it's not correct. And the reason for that is the form is wrong. This needs to be in the form of f of x equals cos negative 2x plus or minus something. That negative 2 in front of the x, right, inside the bracket, it has to be just x plus or minus a number. So if I take pi over 3 and I factor out a negative 2, I'm actually left with negative pi over 6. And it turns out that that, in fact, is the correct answer. X minus pi over 6 means it's going to have a phase shift of right pi over 6 or 30 degrees. So make sure that your equation is in the right form to read information out of it. Otherwise, it may not work out so well for you. All right, for part 6, play in Desmos to see what each of those functions looks like. This is something, honestly, you're better to do it on your own. Just go play with it. Plug in f of x equals 3 sine x, 5 sine x, 22 sine x, etc. See how they change. Or if you'd like, put in a sine x and add a slider for a and play around with it. And I think it will justify it to you. Now this one in particular, I'm going to point out because this is the one that students tend to mess up of the 3 or of the 4 options. And what I want you to get used to is if I put in, say, for instance, sine x plus 6, the d value isn't 6. The d value is negative 6. That's x minus negative 6, which ends up being x plus 6. So when it's plus 6, it's actually left 6. And if it's something like x minus 3, it's actually right 3. And it has to do with this way that we define it here as x minus d. The plus c at the end over here does exactly what you think it would do. Plus 3 goes up 3, minus 2 goes down 2, and so on. Back when we did polynomials, we had that problem with whether you put in an a or a k value, they kind of looked the same. 3x squared and 3x squared basically gave the same function, so we didn't really see a huge difference between those. I think that you will see a very big difference when you're doing it with trig functions. One of them, the a value, is definitely a vertical thing, and the k value is definitely a horizontal thing. Okay, some homework problems down there. And I'm going to let you go now and try those problems and come back if you've got any issues with them. I will point out that it does, in several of the questions, say to do a sketch. For these, sometimes I'll tell you just do them in Desmos or whatever. These ones, I would like you to try and sketch, but be extremely approximate. The one that we did there, just going back, this one, not a pleasant experience. Because of that, seriously, just do a quick sketch. It doesn't have to be point by point accurate at all. I just want you to formulate in your brain what the graph should be doing. Does it go up and down? Does it go side to side? Does it slide one way or the other? What does it do? That's all I want from the sketches. Once you've done your sketch, and enough that you've kind of trained your brain to figure out what's happening, then go to Desmos and check it. But do try it on your own first. You'll actually absorb more if you do it that way. Anyway, have a great day, and I will see you in the next lesson.